Good morning, everybody. I welcome you all to a series of lectures on electronic device and circuits subject. Today, I am going to discuss about the load line analysis, diffusion, and transition capacitances. By the way, I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. So, load line analysis. A circuit supplied with DC power as the external source of the circuit. And we are going to do the analysis for it. And the reactive components of the circuits are made zero, and the straight line is drawn above the voltage and current characteristic curves. So they result in the formation of intersection point referred to as the Q point or the operating point. So there is a straight line that is drawn for this purpose is called as the DC load line. Now let us consider the diode, and it is excited with a DC power supply, external DC power supply, and its resistor is connected in series with the diode. So we are going to do the load line analysis for this diode. And because I am giving positive voltage to the anode terminal and negative voltage to the cathode terminal, so this diode is said to be forward biased. And when we apply a positive voltage to the anode and negative voltage to the cathode, that causes a forward current in the loop. The forward current is called as IF. IF is the forward current. Now applying KVL law around the loop, we get Vn minus IFR minus Vf is equal to 0. So Vf is the voltage across the diode and If is the current through the loop. So from this equation we can write that Vf is equal to Vn minus IFR. So that is the equation 1. So Vf is equal to Vn minus IFR. So in the above equation, suppose if you substitute Vf equal to 0, then we get If is equal to Vf by R. And if we substitute If is equal to 0, we get Vf is equal to Vn. So we are getting 2 points. What are the 2 points? 0, comma Vf by R. There is 1 point. And another point is Vn comma 0. So we are going to put these points on the characteristic curve, and we are going to join these 2 points to get a straight line. So that straight line is called as the load line. So these are the 2 points. Here Vf is equal to 0 and If is equal to Vf by R, and here it is other point. The other point is Vn comma 0. So If is 0. So when If is equal to 0, Vf is equal to Vn. So from this equation Vf is equal to Vn minus IFRL, if we rearrange this equation, we get minus IFRL is equal to Vf minus Vn. So we can say that If is equal to minus 1 by RL Vf plus Vn by RL. So the slope of this line is 1 by RL. So this line is called as the load line. And the intersection of the diode forward characteristic and the load line will give us the operating point, which is called as the Q point. So we can change the Q point by changing the value of the load resistor. So if we change the value of load resistor, the Q point can be made to move on this characteristic curve. So we can choose various operating points by simply changing the value of load resistor. So this is called the load line analysis of the diode. Now coming to the diode capacitances, there are two types of capacitances which come into existence when we deal with the diode. They are transition or the depletion region capacitance, and another is the diffusion or storage capacitance. Now, so this is the depletion region in unbiased condition. That means when we don't apply any voltage to the diode, this is the condition of the diode. So when we do not apply any voltage, initially the holes they move from higher concentration to the lower concentration, and the holes when they cross the junction, they meet with the electrons, and the atoms in N type, they lose their electrons and hence they become positive charged. Similarly, when the electrons cross from the N type to the P type region, the atoms which are in the P type region, they lose their holes, so consequently they become negatively charged. So we get a junction which consists of the immobile charges. This is also called as the space charge region or the depletion region. Why it is called depletion region? Because it is it is not going to contain any charge carriers. It is going to contain only the ions, positive and negative ions. So that is why this is called as the depletion region. And another reason for this is the space charge region. Space charge region. Okay, and when the diode is forward biased, these negative ions which are there at the junction, so they move towards the positive terminal of the battery, and the positive ions which are present in the N-type material or N region, they move towards the negative terminal of the battery. So the positive ions which are there in N region, they move towards the negative terminal of the battery, and the negative ions which are present in the P region, they move towards the positive terminal of the battery. So consequently what happens? The depletion region width, it gets reduced. And similarly, when the diode is reverse biased, the depletion region width increases. Exactly an opposite phenomena takes place, and the depletion region width decreases when the diode is reverse biased. So the presence of these positive and negative charges across junction, it is a function of the applied voltage. So as we see here, if you apply a forward bias, there is going to be a reduction in the number in the positive and negative ion numbers. So if we reduce the forward bias, the number increases. If we increase the forward bias, the number of positive and negative charges, it decreases. So there is going to be a change in the charge with applied forward voltage. So whenever there is a change in the charge with voltage, we say that there is going to be a capacitive effect, because C is equal to dq by dV. So whenever there is a change in the charge with respect to the applied voltage, a capacitive effect is going to occur. Similarly, in reverse bias also, if we increase the reverse voltage, there is going to be more and more accumulation of charge with the increase in the reverse voltage. So in the reverse voltage also, there is going to be capacitive effect. And there are two types of capacitances with the diode: diffusion capacitance and transition capacitance. So diffusion capacitance is active when the diode is forward biased. So this is active when the diode is forward biased. Okay. So the diffusion capacitance, it occurs because of stored charge of minority electrons and minority holes in the vicinity of the depletion region. So a large number of charge carriers which try to move to another region will be accumulated near the depletion region, before they recombine with the majority carriers. So as a result, there is going to be a large amount of charge which is stored on both sides of the depletion region, and this gives rise to the diffusion capacitance. So the diffusion capacitance is given by this formula CD is equal to dQ by dV, where CD is the diffusion capacitance and dQ is the change in the number of minority carriers stored outside the depletion region, and dV is the change in the voltage applied across the diode. Now let us derive the equation for the diffusion capacitance. See, when the diode is uniformly doped, then the depletion region occupies equal portions on P side and N side. So, if Nd is equal to Na, that means if the donor atom's concentration is equal to the acceptor atom's concentration, then we say that the diode is uniformly doped or equally doped, then the depletion region occupies equal space both on P side and N side. So here you are going to have the positive ions, and here we are going to have the negative ions. So this is when Nd is equal to Na. But suppose if P side is heavily doped than N side, then the depletion region occupies more space on the N side, because there is going to be a more penetration by the holes to the N side. So if Na is far greater than Nd, then the depletion region is going to spread more on the donor side, on the N side. So here you will have more and more positive ions, and here we are going to have less number. So this is P and N, and this is a distribution of charge when Na is far greater than Nd. Na is the acceptor atom's concentration, Nd is the donor atom's concentration. So as the acceptor atom's concentration is more penetration takes place into the N region, and consequently the depletion region is more, the spread is more in the N-type region. And in other case, if Nd is far greater than Na, then the depletion region occupies more space in the P region. So this is P region and this is N region. So here we are going to have more spread of the depletion region. Now let us derive the equation for the diffusion capacitance. So diffusion capacitance, as we discussed, it is the capacitance which is prevalent when the diode is forward biased. So when the diode is forward biased, there is going to be injection of charge. So more holes are injected into the N-type region, and electrons are injected into the P-type region, and there is going to be a change in the charge distribution. So this rate of change of injected charge particles with applied voltage, it is called as the diffusion capacitance. So we can say that CD is equal to dQ by dV. Okay, let us say this is equation 1. Okay, so and the diffusion capacitance, it is it depends upon the eta. Eta is 1 for germanium and it is 2 for silicon, and it depends upon the value of eta also. Okay. Now, if you see the various current components in a PN junction, this is the P region and this is the N region. So in the P region, the current flows mainly because of the holes. So the current due to the holes is more in the P region. So, and as the hole current is less in the N-type region because holes are the minority charge carriers in the N-type region. So this is the current due to the holes. So this I call this as IPP, and this one I am going to call this as IPN. So that means this is a hole current in the N region. Similarly, the electron current is more in the N-type region, and as we travel towards the P-type region, it is going to reduce. So this is called as INN. That means the electron current in the N region, and this is INP. So this is the electron current in the P region. So the current at this point junction, we are going to denote it is equal. The current due to holes and electrons is equal at the junction, and it is denoted as IPN0 and INP0. So when we add these two things, we get the total current at the junction. So I is equal to IPN0 plus INP0. So this is the current at the junction. So let us assume that the P side is heavily doped. So when the P side is heavily doped, the current is going to be essentially due to the holes. It is not that the P and N regions are equally doped. Now, for the assumption that the P side is heavily doped, we can say that the whole current is going to dominate compared to the electron current. Then I is going to become, I is approximately equal to IPN0 when P side is heavily doped. Okay. Now the diffusion, when P side is heavily doped, there is going to be a flow of holes from the P side to the N region because of the concentration gradient, and this is called as the diffusion current. So the diffusion current is given by this formula JPX, and JPX is equal to minus QdP into dPn by dx. And dPn by dx is a concentration gradient. Because the P side is heavily doped, so there is going to be a concentration gradient when we travel from the P side to the N side, and because that causes the whole diffusion current, and the whole diffusion current is equal to minus Q dP into dPn by dx, where dP is the diffusion constant and dpx by dx is the concentration gradient. So what is J? J is the current density. So J is equal to I by A. Okay. So we can calculate IP from this. So IPX is equal to JA. And what is JA? J, you can see here, J is equal to minus Q dP into dPn by dx. So this is equal to minus QA dP into dPn by dx. So this is equation 3. Okay. Now, Pn, I told you that the concentration gradient, the whole concentration is not uniform across the junction. So, in the P region it is more, and as we travel towards N region it is less. So, the concentration gradient is like this. The concentration gradient of holes is like this. So, as we move away from the junction, it is less, and near the junction it is more. So we can say that it follows exponential fashion. So Pnx is equal to Pn0 into e power minus x by Lp, because there is exponential decay of hole concentration as we move away from the junction into the n side. So dp, and let us do the derivative of this. So differentiating this, we get dpn by dx equal to minus 1 by Lp, minus 1 by Lp into Pn0 into e power minus x by Lp. Okay. Now let us substitute this in equation 3. In equation 3 we have this dpn by dx, and let us substitute this dpn by dx in equation 3. Then we get so substituting this in equation 3 we get Ipx is equal to minus QAdP, and dpn by dx is minus 1 by Lp into Pn0 into e power minus x by Lp. Okay. So let us say this is equation 4. Now at the junction x is equal to 0. So at x is equal to 0, we get Ipx becomes Ip0. So Ip0 is equal to minus QdP into minus 1 by Lp into Pn0. So this becomes QAdP by Lp into Pn0. QAdP by Lp into Pn0. So this is equation 5. So Pn0, from this we can say that Pn0 is equal to how much? Pn0 is equal to Ip 0 into Lp by QA dP. So this Ip0, let us write it as I. So Pn0 is equal to ILP by QA dP. So this is equation 6. Now excess minority charge carriers on n side, it is given like this. The excess minority charge Q on the n side so it is given by, we have to take the concentration of holes, then multiply it by the area, then multiply it by the charge per holes. Okay, so that is given by Q is equal to AQ. A is the area and Q is the charge on the hole. So that is Pn0 into e power minus x by Lp, because there is a concentration gradient. So this, which is given by this, and this one we have to integrate from 0 to infinity. So we have to calculate what is the total amount of charge which is present in the n-type region. So we have to integrate in the limits 0 to infinity, and we have to take the concentration gradient of the holes, which is nothing but Pn0 into e power minus x by Lp, and this one we have to multiply with the area A, and Q is the charge per hole. So this one we have to integrate in the limits 0 to infinity. So if we integrate this in the limits 0 to infinity, we get this as Q is equal to, when we put infinity into e power minus x by Lp, that is going to become 0. And minus of minus, we are going to get Q as AQ and Lp Pn 0. So this is the equation 7. So Q is equal to, so that way we are going to get. So Q is equal to AQ e power minus x by Lp, and when we integrate, we are going to get Q is equal to AQ Lp into Pn 0. So this one, and we have to take the derivative of this, and this is equation 7. So Q is equal to AQ Lp Pn 0. Pn 0 earlier we have calculated, and Pn 0 is equal to ILP by QA dp. So take this from equation 6 and put it into equation 7, then we get ILP by QA dp. So this one we are going to get this as I LP square divided by dp. So this is the equation 8. Now let us call this LP square by dp as tau, which is the mean life of the charge carriers. So we can say that Q is equal to tau I. Q is equal to tau I. So what is dq by di? dq by di is equal to tau. Now what is the diffusion capacitance CD? The diffusion capacitance CD is equal to dq by dV. So we can say that dq by dV is equal to dq by di into di by dV. And what is dq by di? That is nothing but tau. So CD is equal to tau di by dV. Okay. And what is the diode equation? We know that the diode equation I is equal to I naught into e power V by eta Vt minus 1. That is the diode equation. So let us take the diode equation and differentiate the diode equation with respect to voltage. So the diode equation is I is equal to I naught into e power V by eta Vt minus 1. So this is a diode equation, and let us differentiate this with respect to voltage. Then we get di by dV is equal to I naught into e power V by eta Vt into 1 by eta Vt. So let us substitute this, then we get, so we can say that di by dV is equal to, say, I naught into e power V by eta Vt. So because neglecting the reverse saturation current, so di by dV is equal to, is approximately equal to I divided by eta Vt. So this is equation 10. Now let us substitute this equation 10 into equation 9. This is the equation 9. So then we get CD substituting substituting 10 in 9 we get CD is equal to tau I by eta Vt. So this is the equation for the diffusion capacitance. So if we see the diode, as we increase the forward bias voltage, the depletion layer width decreases. So as the depletion layer width decreases, there is going to be more and more amount of current, and I is going to increase. Thereby, the diffusion capacitance increases as we increase the forward bias. So this is all about the diffusion capacitance. Now coming to the transition capacitance, the transition capacitance is active when we apply the reverse voltage. So when we apply the reverse voltage, the charge concentration across the immobile ions at the junction, their number, it increases. So that is going to cause more and more width of the depletion region. So as the depletion region width increases, the transition capacitance it decreases. So transition capacitance, it is active in the reverse bias. So the depletion region of the PN junction diode, it has high resistance. So the depletion region acts like the dielectric or the insulating material. So the transition capacitance, it is mathematically written like this: Ct is equal to epsilon A by W, and epsilon is the permittivity of the semiconductor, and that is equal to epsilon naught and epsilon R, and epsilon naught is the permittivity of free space, which is 8.849 into 10 to the power minus 12, and the epsilon R is the relative permittivity of silicon or germanium, and that is equal to 16 for germanium and 12 for silicon. And A is the area of plates for P-type or N-type region, and W is the width of the depletion region. So this transition capacitance, typically it varies from 80 picofarads. It varies from 80 picofarads to 5 picofarads as the reverse voltage changes from 2 volts to 15 volts. So as the reverse bias changes from 2 volts to 15 volts, the transition capacitance varies from 80 picofarads to 5 picofarads. Now let us derive this formula for the transition capacitance. Derivation for Ct. Ct is nothing but the transition capacitance. Now in this case, let us consider a PN diode which is not uniformly doped. Let us assume that the N side is heavily doped. Earlier we have assumed that the P side is heavily doped. Now let us assume that the N side is heavily doped, and let us do the calculation for the transition capacitance. So assumption is N side is heavily doped. So when N side is heavily doped, what happens? The depletion region spreads more into the P-type region, and whatever WP is there, is approximately, we take it as the width of the depletion layer. So the width of the depletion layer, W, is equal to the width of the depletion region which is present on the P side plus the width of the depletion region which is present on the N side. So W is equal to WP plus WN, and as N side is heavily doped, so the depletion region essentially presents in the P-type region, and we can say W is equal to WP, approximately is equal to WP. Okay. Now with this assumption, let us do the derivation for the transition capacitance. So the transition capacitance, by the Poisson's equation, we can say that the relation between the potential and the charge density is like this: d square v by dx square, d square v by dx square is equal to qNA by epsilon. So this is a Poisson's equation. Now to see the actual voltage value, what we have to do? We have to integrate this 2 times. So this is equation 1. Now integrating once, we get dV by dx. So that is equal to, when we integrate this once, we get qNA by epsilon into x. So this is equation 2. And if we differentiate this again, if we integrate this again, we get V is equal to qNA by epsilon x square by 2. So this is equation 2. And this integration we have to do in the terminals, in the limits 0 to W. Then we get V as qNA by epsilon into W square by 2. So this is equation 3. So we have taken the Poisson's equation and then we have integrated 2 times, and in the limits 0 to W. So we get V is equal to qNA by epsilon into W square by 2. So this is a diode, and essentially we have more spread into the p-type region because the n side is heavily doped. Okay. So this is WP. Okay. Now at x is equal to W, at this point at x is equal to W, the barrier potential is high. So the barrier potential spread, if you see, the barrier potential slowly it rises and it becomes more. So the barrier potential, we can say that VB is equal to V0 minus V, where V is a voltage which is applied externally. So and V0 is the contact potential. Now in this case, as we have applied a reverse voltage, we say that VB is equal to V0 plus V, because for reverse voltage V is negative. So VB is equal to V0 plus V, and contact potential is very small. So essentially VB is equal to V approximately. So we can say that the barrier potential, what is V? V is equal to qNA by epsilon into W square by 2. So we can say that VB equal to qNA by epsilon into W square by 2. So this is equation 4. So from this equation 4, we can infer that the width of the depletion region, it is proportional to VB, or we can say that W is proportional to square root of VB, because we are having W square here. So we can say that the width is proportional to square root of the barrier potential. Now let us see what is the amount of charge in the junction. So the amount of charge in the junction, it is given by Q is equal to, we have to take the acceptor atom's concentration, because we are calculating for the n side, multiplied by the volume and multiplied by the charge per carrier. So let us take the charge per carrier is Q. So for whole it is 1.6 into 10 to the power minus 19. So Q is equal to NA into volume into Q. So that is the net charge. So this is equal to NA. What is the volume? area multiplied by the width. So area is A and width is W, and this is Q is the charge carrier. So this is equation 5. Now differentiating equation 3 with respect to V, we have, what is equation 3? This is equation 3. V is equal to QNA by epsilon into W square by 2. So if we differentiate this with respect to T, this side we get 1 and here we get another thing. Okay. So differentiating 3, differentiating equation 3 with respect to V, we get, on left hand side we get 1 and we get dV by dV equal to d by dV into QNA by epsilon into W square by 2. So 1 is equal to d by dV into, so 1 is equal to d by dV into, 1 by 2, there's a W square by 2, so let us take the 2 outside. So Q is constant, QNA by epsilon into W square. So we get 2W into dW by dV. So dW by dV is equal to epsilon. So this 2 and 2 they get cancelled. So we get dW by dV is equal to epsilon divided by QNA W. So this is equation 6. Now let us differentiate equation 5 with respect to V1. We get differentiating equation 5 with respect to V1, we get dQ by dV equal to NA into A into W into dQ by dV. So dQ by dW by dV. But dW by dV we have already got in 6. So we get, substituting for equation 6 here, we get dQ by dV, substituting 6, we get dQ by dV is equal to NA into AQ. And what is dW by dV? That is equal to epsilon. It is there here. So epsilon by Q NA W. So Q they get cancelled, NA they get cancelled. So we get dQ by dV equal to epsilon A by W. So this is a formula for what is dQ by dV? There is nothing but the capacitance, which is a transition capacitance. So we can say that CT is equal to dQ by dV, and that is equal to epsilon A by W. So this is a formula for the transition capacitance. So this is how we derive the formula for the transition capacitance. So the transition capacitance, it is essentially because of the reverse bias, whereas the diffusion capacitance is because of the forward bias. So in today's lecture, we have discussed about the DC load line, which we have applied Kirchhoff's voltage law, and we have drawn the DC load line, and the intersection of the DC load line with the forward characteristic of the diode has given us the Q point, and the Q point can be changed by varying the load resistance in the diode circuit. And also we have discussed about the two types of capacitances, transition capacitance and the diffusion capacitance. Transition capacitance occurs when the diode is reverse biased, and as the reverse voltage increases, the depletion layer width increases, thereby the transition capacitance value it decreases. And the diffusion capacitance comes into picture when the diode is forward biased. As the forward bias increases, the depletion layer width it reduces, so thereby the diffusion capacitance it increases. So with this, I conclude today's topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.